All right. So we're going to start here with number 2, as voted by the class, and we'll see how it goes. So, first thing I'm going to do is I have a total of 3 force diagrams here. And actually, technically, this problem, remember if you're doing a different problem, that's fine, but just try to keep it down a little bit. Technically, I should do 6 with this one, because during the first case, it's not accelerating, and during the second case, it is accelerating. But I can just kind of use the first, I'm not going to draw 6. Deal with it. Oh, number 2, sorry. Thank you for catching it. And so my system is both of these together, and then I'm going to do individual force diagrams of the 2. All right, and I said I have a cord up, a cord down, and a cord up here. So let's see, how do they label them? Now, how many of you have the same mass for each of your buckets? Is it everybody? Okay. So I'm just going to, so mine is 3.3 kilograms, so let's see. I have a weight total down. Oh, this is like identical. Yeah, it's like the first one we did, except it's simpler because it's only 2 objects. Okay, so that would be the correct force diagram for the system. No acceleration. And in the second part, I'm just going to add in an acceleration, but we'll do that afterwards. Then the individuals, I'd have FT1 up. Let's call this FT2. This would be FT2 for the bottom one. Oops, and there'd be a weight down here. And here there would be a weight down. It's an FT. So those would be my 2 individual force diagrams. When we do the second part, so I'm just going to put it in here as a dotted line. When we did the second part, what we need, let's see, which way am I accelerating? Upwards. Yeah, upward. Because it says pulled upwards. No, I just wanted to get this out of the way. For part B, I'd have the exact same diagrams, except I'd have an acceleration upwards. Alright, so it'd be for part A, it's without the acceleration. For part B, exact same diagrams, but with the accelerations. Alright? So, now, I think what a lot of people, the connection that a lot of people are having a hard time with is realizing that when I do the free body diagrams, those are the exact same as my equation. I only have one equation in the whole section, right? F equals ma. Sum of the forces equals mass times acceleration. I use the free body diagrams are that equation just in a picture rather than in math, rather than written in mathematical terms, drawn as a picture. These are just to help me make sure I understand the problem. So that's why I go from these to the free body diagrams, which are really part of my mathematical work. So let's see, what do they want me to find out? The tension in each cord. Okay? So in this to find the tensions, the system does me no good because it doesn't have either tension on it, right? Well, it has one of the tensions. I could solve it that way. So I could use the system, sorry. Or I could use the upper bucket has both tensions on it. The lower bucket only has one tension on it. So I could use, if I wanted to find, the lower one I could use to find FT2. The middle one I could use to find either one, but not both at the same time. And the system I could use to find FT1. Which one do you guys want to find first? FT1 or FT2? FT1? Okay, then I'm going to recommend let's use the system to find that. Alright? So, I need to start off drawing a picture of my equation. I do that in the free body. So, I'm going, I need to write my inertia next to it. I've got both buckets in my system, and I'm told the inertia of each bucket for me is 3.3. That means the inertia of my system for me is 6.6 kilograms. I got that by adding 3.3 to 3.3. Then, in my system, I have FT1 up. I have the weight total down. And that's it. Right? Well, that's a pictorial view of sum of my forces equals MA. This equation can be drawn as this, or written as FT1 minus FGT equals my inertia, 6.6 kilograms, times my acceleration, which is 0 meters per second squared. Writing this and drawing this are the exact same thing. You see that? Okay? They're both just different ways to represent Newton's second law here. Sum of the forces equals MA. Sum of the forces equals MA. Oh, the whole thing? Both of these are just the same thing because they're just different ways to express that equation. Here, on the right here, I wrote it in math. On the left here, I drew it as a picture. But they're both the exact same thing. It's kind of like, you know what? Hello, and then in Spanish it's hola, and in French it's, and in German it's, I knew she was in the German club. Huh? Because some people that will make sense, and some people this will make sense. So, I require both because I think more people will have an easier time going from the force diagram to this and then to this than directly doing the numerics in the drawing. But you can do the numerics in the drawing. Okay? So. All right. Sure. Yep. Yep. No. Well, and what I said is I decided that up was positive. Right? You were saying, what if down was positive? And that would come out exactly the same. As long as you're consistent there, you're fine. Yeah. So, let's see. I don't know FT1. Oh, but I know that FT1 equals FT total. And I remember from my equation sheet, remember I've got one equation and a couple of identities. One of the identities says that the weight is the mass times the gravitational field strength, little g. So let's see. So the system has a mass of 6.6 kilograms, and it's on Earth, so little g, the gravitational field strength is 9.8 newtons per kilogram. So my FT1 is going to be, you can't do that in my head, so 6.6 times 9.8, 64.7. 64.7 newtons. Yes? No? Okay. So now I need to find FT2. That's FT1, the top chord, yep? Yep, chord. Now I need the lower chord. I'm going to use the bottom bucket. Is that okay? So on the bottom bucket, I'm going to draw the free body of it, just because that makes some sense to me. So remember, my equation is sum of the forces equals ma. I'm going to first express it as the free body. Dot F sub g, FT2, and that has an inertia of 3.3 kilograms. So visually, I've expressed sum of the forces equals ma. From my problem that told me each bucket has a mass of 3.3 kilograms. Yours is different. And now I'm going to write that in math rather than as a picture, and write that FT2, because I'm going to take up as positive, I know you guys like that, minus FG equals my mass, 3.3 kilograms, times my acceleration, 0 meters per second squared. Also, FT2 equals FG. So FT2 equals my mass, 3.3 kilograms, times the gravitational field strength, 9.80 newtons per kilogram. Oh, you know what? I messed up. Oh, no, I didn't. So, well, let's see. 3.3 times 9.8, 32.3. All right, see you after lunch for the second half of this problem. Let's continue back here with going on to part B of this problem. So in part B, it's accelerating upwards. So you remember our force diagrams now would have an acceleration upwards there. So I'm going to go through the same procedure, but this time with an acceleration. So again, I have my one equation, sum of the forces equals ma. I'm going to draw it first. Draw the equation. It's still 6.6 kilograms. But this time, and we still have the same forces, FT1, FG total. The only difference is this time we have an acceleration upwards, and they tell me my acceleration is 1.80 meters per second squared. So 1.80 meters per second squared. So now that I've written it as, or drawn that equation, now I can write that equation. FT1 minus FT total equals 6.6 kilograms times 1.80 meters per second squared. So FT1 equals FGT plus 6.6 kilograms times 1.80 meters per second squared. And from doing the earlier one, I know what I know the total weight of the system, right? Yeah. And then I would move on to my, again, go down to my bottom one, and same equation, draw the forces this time. It was just FG, it was FT2, it was 1.80 meters per second squared, and the whole thing had an inertia of 3.3 kilograms. And if you can draw the equation, you should be able to write the equation mathematically, right? Yes? Yes. Alrighty. And then all you're solving for is FT2. So, I'm going to trust you guys to do that one. And I'd kind of like to move on to number 4 here. Some people ask for it, haven't had a chance yet. In number 4, we've got these two boxes. We've got accelerate. We've got, do we have acceleration? On the surface. Yes, we have acceleration. And then we have these interior forces. And we didn't have one set up exactly like this on the, when we went over this, but it's very similar to pulling. So, this is number 4. Okay. So we have our system here. I'm going to draw like that. We should have, then we're also going to do our individual crates. And then they also, let's see, they asked us something else. Oh, they asked us to reverse it, so. Okay, let's see. Mass 1 is 50 kilograms, mass 2 is 130. I'm going to actually write that right in here this time. That's another way you could do it. Okay, just writing the masses right in them. So that means, what's the mass of the system? 180 kilograms, right? So, we haven't been including the inertia or the mass in the system, or the others. You could, if you wanted to. I haven't put the weight yet, but I put the mass. Well, let's see, one of the boxes is 50, and the other is 130, so I combined them to be 180. All right? So I'd have the total weight down. I'd have a normal force up. I'm pushing with a force, and in my case, in all cases, it's 620 newtons. And there must be a frictional force here. We'll call that FF total. And then there would be an acceleration. So each crate is going to have that same acceleration. That's why they're a system. This one, let's see, would have FG1, we'll call that. FG2, F normal 2, F normal 1, 620 newtons. Friction force 1. Let's see if they're touching. So if the 50 kilogram crate is pushing on the 130, right? Some force F. What's happening? What's the 130 doing to the 50? Pushing back on it. How does that force compare to the other force? Same, right? Newton's third law. And then there would be a frictional force here, F2. So those would be the force diagrams for this that would give you full credit. Okay? And they want us to figure out the acceleration, right? And the acceleration here, let's see, I'm going to use the system to do the acceleration. It seems to have the least things I don't know. So, start with my equation, of course. Draw what goes into my equation. System which has 180 kilograms inertia. It's going to have F sub G total, force normal total. I'm going to draw my 620 newtons facing that way just to clean it up a little bit. Friction force total, and then my acceleration. Good? Do you need me to do the free body diagrams in the X and in the Y direction? No? Okay. So I'm gonna do the X direction over here. Actually, let's do the Y direction first. Y looks a lot simpler. In the Y direction, I have force normal total minus force gravity total equals 180 kilograms times 0. It's not accelerating vertically. Okay, so the force normal total equals the weight total. Oh, okay, and that would be 180 kilograms times 9.80 newtons per kilogram. Right? Yes? No? Yes, somewhere around about 2,000, a little under. And now in the X direction of the system, let's see, I have 620 newtons minus the frictional force total. Those are my only forces. That must equal 180 kilograms times A. Good. Oh, okay. So, let's see, 620 newtons minus mu force normal. Let's see, the normal force that's creating the total friction is the total normal force. Equals 180 kilograms times A. Oh, I know some of those things. Do I know mu? 0.15. Good. So 620 newtons minus 0.15 times, oh, I know that, 180 times 9.80 newtons equals 180 kilograms times A. Oh, so I can, maybe I should figure out what that number is. Let's see. Clear 620 minus 0.15 times 180 times 9.8. 355.4. So I get 355.4 newtons equals 180 kilograms times A. That divides both sides by 180 kilograms. And I get A equals 1.97. You got a negative number? That would be difficult to do. I think you made some math mistakes. That or you forgot the 0.1. Ah, yeah. So, let's see. We got the acceleration. I think it's right. Calculate the force each crate exerts on the other. So that's the force F that we diagrammed up here. Way back up here. Well, I need to figure out what I'm doing. Hold on. I think I'll use the 130 kilogram crate next, because that seems to have less forces on it. So I'm going to use the 130 kilogram crate to find the next one. So I got this, and it's 130 kilograms. Force normal 1. Force 1. F. Frictional force 1. And the acceleration. So there's the drawing of my equation, right? Otherwise known as the free body. Just in the essence of time, can everyone see why the force normal 1 would equal the weight 1, which would be 130 kilograms times 9.80 newtons per kilogram. So force normal 1 would equal, oops, 130 times 9.8. 1274. Alright. So, now I need to do the x direction here, which would be F minus FF1 equals 130 kilograms times A. Oh, I know A. 1.97, I think it was 444. Yep. Meters per second squared. equals FF1 plus 130. There's no wrong on that. 130 times 256.6.7. 256.68 U force normal 1 plus 256.68. I did the math. I did 130 times 1.97. Uh, 0.15, 1274. All right. I always do something like that. Oh. And just calculate that, and I'd get F. Okay, so that brings up the last part of the problem, which is what would, if the crates were reversed, what would happen? Well, if the crates were reversed, no, they're not, they're saying you're still pushing, but rather than the 130 being on the right, it's now on the left. It wouldn't change the acceleration, right? Because it's not going to change the system. It would change how much the two crates pushed on each other. Right. Exactly. And so what would change here is this force is these two diagrams where they essentially would be very close to the same, except you'd swap the 50 and the 130, which is going to change your inertia, which will change the force in between them. All right? But it's not going to change the acceleration.